Hi, Dr. C here. Physics Made Simple by Dr. C. That's me, Incline Plane. What I want to show you are some basic fundamentals that you need to master, and you need to understand these things. If we have an incline, we usually draw the angle of the incline as theta, and one has to realize there's some geometry here that kind of helps us break things up. So if this angle's phi, this angle's theta. So what we typically do is that we want to get the force components of the weight, mg is straight down, we want to get that in a direction perpendicular to the incline and parallel to the incline. So this angle actually is theta, according to this trigonometry that we see here, because this angle is 90. So you can convince yourself that. But you might want to know, why is this? This is mg cosine theta, and this is mg sine theta. And my daughter asked, she said, "Dad, why do you draw it down here?" And then she finally, the light went on. She goes, "Oh, I see. You're actually breaking this weight, mg, into these two components. But in reality, this is where it's applied. It's applied to the center of the mass m. So mg sine theta is applied to the mass down the incline. So let me redraw that. So it's mg sine theta is the component of the weight that's straight down to the center of the earth. The earth is here. We draw it straight down to the center of the earth. And the incline sits on the earth. So this is the way it is. Mg sine theta is down the incline, and mg cosine theta is perpendicular to the incline, and it's down. So now we ask, what else? What other forces do we have? So let's just take a look at this. Let's redraw this again. You got to draw the free body diagram. So we have a weight, and let me walk you through it. We have a weight that has a mass m, a block, say, and it's sitting on the incline. And it doesn't fly off. It just slides on the incline. When we let go, it slides down the incline. So we have to draw the free body diagram of the mass on that mass m. What are the forces on mass m? So you have mg down, but there's also this normal force that's drawn upward, perpendicular to the inclined plane. If you have friction, let's draw some friction on here. So it's going to move down the incline due to gravity, due to this component, mg sine theta. And friction is going to be in the opposite direction of its motion, and it's going to be equal to the coefficient of friction times the normal force. So if you're solving for a problem on an incline with friction, you need, as in all cases, you need the normal force if you're dealing with friction. So just suppose the coefficient of friction is mu is equal to 0.1. So what's the normal force? Well, we have to get the normal force, and we also get the forces along the direction of the incline. So down the incline, it's mg sine theta, and this is mg cosine theta. So those are all the forces that act on the mass, but we have to use Newton's second law. So let's just do this. plus y is down, plus x is down in the down direction, down the incline, plus x. Let plus y be up. Plus y is up. I usually draw it back here, but it doesn't matter where you draw it. It's just up. So the sum, and it sets your origin, but we're not going to worry about the origin right now. So we have to do the summation of the forces in the x direction. That's what this sum sign is. Summation of the force components in the x direction is equal to the mass times the acceleration in the x direction. But I'm not going to put the x here. What about the y direction? Summation of the forces in the y direction. And what's that going to be equal to? That's equal to the mass times the acceleration in the y direction. But what is the acceleration in the y direction? That is the direction perpendicular to the inclined plane. The acceleration is 0. It's 0 because it doesn't fly off the incline. It just stays there in the y direction. There's no acceleration, no change in velocity. If it starts at initial velocity in the y direction of 0, we just write that. Vy naught is 0. Vx naught, the initial velocity in the x direction, is also 0. So it starts from rest. That means we have an equation. The normal force is in the plus y direction and minus mg cosine theta, which is equal to 0. Well, that gives us the answer for the normal force. The normal force is mg cosine theta. You're used to mg as being the normal force on a flat plane. Well, when theta is 0, if theta equals 0, then cosine of theta is 1, and you get just mg. So when it's a flat inclined plane, the normal force is just mg. But when it's inclined, it's mg cosine theta. So that's something important to know. Therefore, the force of friction is equal to mg mu times mg cosine theta. So now we can work, so this is equation 2, but I'm solving it first. Equation 1, let's go back to that. Summation of the forces in the x direction is equal to the mass times the acceleration in the x direction. We want to get the acceleration in the x direction. So let's write this in here now. This goes into mg sine theta is in a plus x direction, mg sine theta. And then the friction is in the minus x direction, so we put a minus sign, mu mg cosine theta. And that's all equal to the mass times the acceleration in the x direction. Isn't this beautiful? When we write it algebraically like that, the masses divide out. You don't even need to know the mass. Why? Because under constant acceleration, which is generally like free body, you don't need to worry about the mass. It's just the acceleration is g. So in that case, there's no mass involved. That's why we have it here. When you drop a ball, the acceleration is g down. So in this case, the acceleration, we just solve for it. It's equal to g times sine theta minus cosine theta with a mu in front. That is the acceleration. So if you have no friction, then this second term goes away, and it's just the acceleration is g sine theta, which is basically this due to this component of the force, mg sine theta. So that's how you do this. So the acceleration down the incline is g times sine theta minus mu cosine theta. There you go.